Hello everyone, welcome to today's class. This is Teacher Simon taking you through A-Level Mathematics 9709/43 for May, June 2025. And this is mechanics. Question 1 is coming from momentum. Two particles P and Q of masses 0.1 kilograms and 0.3 kilograms respectively are at rest on a smooth horizontal plane. The P is projected directly towards Q with a speed 4u meters per second. At the same instant, Q is projected directly towards P with a speed u meters per second. After P and Q collide, P moves with speed 2 meters per second and Q moves with speed 4 meters per second. Part A, find the two possible values of u. Okay, now we are having our two particles here. Okay, this is P 0.1 kilograms, this is Q 0.3 kilograms. They are lying on this horizontal plane. Then we are also having these two after collision. What happens to them? We have P and we also have Q. 0.1 kilograms, 0.3 kilograms. Now, we are going to consider two cases, okay? First of all, U of P, this one is projected forward, and then this is 4U, and then U of Q, I will say this is negative U, okay, because it is moving in a negative direction. Then, remember, momentum is product of mass and velocity is a vector quantity, so direction has to be put into consideration. Now, here we have case 1. Okay, case 1, we can see these two can move all this side. Okay, they can move all this side to the right. So I can have VP going this way. Then I can also have VQ is also going this way. Okay, but VQ, this one is 4 meters per second, and then this one is 2 meters per second. Okay, it was given here. Now, case 2, since P here is lighter than Q, it can knock Q and then rebounds. You see that? So case 2, I can see P can move this way. Okay, and that means its velocity is now going to be a -2. You see that? Then for Q, it can move this way. I'm going to leave it to move this way. Why? Because P here has gotten a bigger speed by the time it hits Q. You see it. It is 4 times this one. So I'm going to let it continue to move this other side. So you should move there. Now, what are we having here? This one is going to be again 4 meters per second. Now, using the principle of conservation of momentum, our case 1, like I've said, okay, P and Q move in the same direction. So MP UP then plus MQ UQ is equal to MP VP, then plus MQ VQ. Then here we shall have 0.1 times 4U, then plus, this will be 0.3 times, now this one will be a negative U, okay, because it is moving in the opposite direction. Mass of P is 0.1, then times, this one will be a 2, and then this one here will be 0.1 times a 4. So what shall we have here? This is 0.3U, this is 0.4, so when you subtract them, you'll get 0.1U, right? And then this other side, we have 1.2, no, it is going to be 0.2, then plus 0.4. There must be a mistake here, pardon me. Mass of Q is 0.3, then times negative, it's a positive, times the positive 4. So this one is going to be 1.2, then plus 0.2, that will be 1.4. When we divide all through by 0.1, that means U becomes 14. Okay, now we also go to case 2. Case 2, P and Q move in opposite directions after collision. In other words, P rebounds. Okay, so again we are using this one here, so just put it there, and since this one rebounds, P rebounds, this one will be a negative 2 here. Okay, then the other one will remain. So this means this is 1.2 minus 0.2, we shall get 1.0. So I'll put here 1.0. So 1.0 divided by 0.1, this one gives us a 10. So the other value of U is 10. Then next, find the largest possible loss of kinetic energy. If they say loss in kinetic energy, then you should know that the initial kinetic energy, total initial kinetic energy, is bigger than total final kinetic energy. Okay, so we can have total loss in kinetic energy, and I'm going to consider, let's say, case 1. When I consider case 1, what shall we have here? Total initial, we shall have a half times what is the kinetic energy in relation to P. So we shall have a half M, the M is 0.1, and then its velocity is 4U. So 4 times what? 4 times 14. The 14 we got here, right? But then we shall square that. Then plus the kinetic energy for Q is going to be a half, then times the mass is 0.3, and then its initial speed is 14, then squared. Okay, then after that, this is all the total initial kinetic energy, then minus the total final, we shall have a half, then times 0.1 times, we have 2 squared, then plus the one for Q, 0.3, then times, we have 4 squared. So what do we get here, then minus what is here? 0.5 into 0.1, then times 4 into I mean, it has to be 4 times 14, then squared. This one gives us 156.8. So 156.8, then plus 0.5 times 0.3, then times 14 squared, 29.4, minus, then inside here, this is a 4 times 0.1, that will be 0.4, divide by 2, that will be 0.2. And then this is 16, divide by 2, that will be 8. 8 times 0.3, that will be 2.4. So this one will give us 156.8 subtract, plus 29.4 minus 0.2 minus 2.4. The answer is 183.6, 183.6 joules. Okay, that is for case 1, and that is the one we are going to take, okay, because that is the one that is going to give us the what? The biggest, because u here is bigger. You see, it is 14. So now when I put 10, remember it is total initial kinetic energy. So here, if we have 10, then 10, okay, automatically this one is going to be, with the 10, we are going to get a smaller value. So we don't need to waste time there, okay. So we leave it at that point. So therefore, our answer is 183.6. Question 2, we can see connected particles here. A van of mass 4,500 kilograms is towing a trailer of mass 350 kilograms along a straight horizontal line. The van and the trailer are connected by a light, rigid tow bar, which is parallel to the road. There are resistance forces X newtons on the van and 120 newtons on the trailer. The driving force produced by the van's engine is 2,500 newtons. Then the tension in the tow bar is T newtons, and the acceleration of the van is 0.4 meters per second squared. Find the value of X and the value of T. Now, I'm going to draw a small sketch here. This one is going to be my trailer. It is being towed by the van. Maybe this is the van. So as it is towing it, this one has, remember, this is my van and this is my trailer. Then there's a driving force, okay, 2,500 newtons. Then there is tension in this tow bar. This tension will be pulling this van behind, and it is that same tension that will take the trailer forward. And then they say there are resistance forces of X newtons on the van. So I'll put here, there is a resistance force of X newtons. And then on the trailer, we have 120 newtons. Okay, now we are going to use F is equal to MA. And when we look at the forces that are acting on the trailer, we can have the two forces. We have the tension and then the 120. So we shall have the net force taking the trailer forward will be tension, then minus 120, which is equal to the mass of the trailer is 350. Okay, 350, then times the acceleration is given as 0.4. So this system is moving forward with an acceleration. That means T is going to be equal to 350 times this 0.4. Then when we take this one forward, we shall get an addition here, 120. So meaning our t then will be equal to 120 plus 350 times 0.4. So altogether, this one gives us 260 newtons. As simple as that. Then next, I'll now look at the forces which are acting on the van. I'm still going to use F is equal to MA. So since it is going forward, that means this driving force is bigger than these two resisting forces. So we shall have 2500, then minus X minus T, then this one is equal to, okay, the mass is 4500, then times A, which is 0.4. So what are we looking for? X. This will be 2500 minus the tension. We have gotten it as 260. Then we shall bring this one this other side. Remember, we are making X the subject of the formula. So minus 4500, then times 0.4. Then this one will be equal to our X. Then what will be the answer here? So X will therefore be equal to 2500 minus 260, then minus 4500 into 0.4. And this one gives us 440. So that is 440 newtons. As simple as that. Question 3 is coming from kinematics. The diagram shows a velocity time graph which models the motion of the particle. The graph consists of 3 straight line segments. The velocity of the particle at time t seconds after passing a fixed point O is v meters per second. The particle leaves O with a velocity of 5 meters per second and accelerates at 0.75 meters per second squared for 20 seconds. So they are talking about this one here. The particle then decelerates for the next 30 seconds. This one here. Now these are 20 seconds, then another 10, so up to here. At 40, at t is equal to 40, the velocity of the particle is 0. That is why it is crossing this t-axis here. After t is equal to 40, the particle starts to travel back to O, coming to rest at O after t seconds. So this is the one here. Okay, then they are saying part A, find the value of t. Now, we are going to consider, first of all, this first segment from 0 to 20. Okay, we don't know the speed here. Now, using v is equal to u plus at. V here, remember the initial speed is 5. The acceleration here was given as 0.75. So 0.75, then the time taken is 20. This one will give us 15, then plus 5, that one will be 20. Okay, 20 meters per second. Then when we look at the second segment from 20 to 40, okay, we need to know the deceleration. Okay, from 20 to 40 seconds, again using v, which is equal to u plus at, v minus u over t. So the final here, when it crosses the t-axis, that is 0. Then the initial is this one we have gotten here, which is 20. Then the time taken here is, the time taken is 20. Yes, so it is 20. Since this one is a straight line, gradient of a straight line is always constant. So it is the same deceleration. So from here up to here is all the same deceleration. Okay, so I didn't consider from here up to here the time interval being 20 to 20 to 50, which is 30 seconds, because I don't know this value here. Okay, so I used this one here in order for me to get the deceleration, this being a straight line. And remember, gradient of a straight line is always constant. And on a velocity time graph, we are seeing change in the vertical axis, which is the velocity, and then change in the t-axis, that is the time, and that one is going to give us acceleration. You see, so gradient on a velocity time graph is acceleration. Okay, all right, so this one gives us negative 1 meters per second what squared. Okay, now having gotten these ones here, then I can proceed to find the value of t. Now, this one being a velocity time graph, the distance traveled forward is equal to the distance traveled backwards. You see that? So I will say the distance forward, because the particle is coming back to the same point, not so? So distance forward is equal to distance backward. Okay, and you know that on a velocity time graph, the distance traveled is the area under the graph. So here we shall have, when we look at this one, it is a trapezium here, then there is a triangle here, and then there is another triangle here. You see that? And actually before that, because we shall need to get the triangle here, the area of this triangle here, then we need to get the V here. You see that? Okay, so I need to find the value here such that it will give me the height of this one. So I need to consider the third segment. So allow me extend and put this one down. So let us have the third segment from 40. Okay, from 40 to, in fact, let me reorganize this, put this one here, then put these ones under this one, then now let's go to 40 less than t less than or equal to what? 50. So here now again we have acceleration, which is equal to v minus u over t, over t. The acceleration, we have seen it is -1. Gradient on a straight line is always constant. Then the final is this v, which we don't know, right? So that is v, then minus the initial is going to be a 0 here. Okay, so 0, then over the time taken, which is v. So when I cross multiply, then v is going to be equal to -10. You see that? So here it is -10. All right, now let's proceed with what we had started on here. So this one, the first one, is a trapezium. So it's a half h into a plus b, and h is the height, that is the length between, that's the distance between the two parallel sides. So this is a parallel side, and this is a parallel side on the trapezium. So this is the height, which is 20. So I will have a half times 20, then into the parallel sides. One is 5, then the other one is this v we got at first, which is what? 20. You see that? Okay, so we'll put a 20 here. This is a 5, then plus the 20, then plus the next one is a triangle here. So we shall have a half times the base is 20, then the height is this one here, is also 20. Okay, so we shall have a half times 20, then times 20, and then After that, what are we going to have? I'm going to get the whole of this as one thing, okay? One triangle. So I will have a half. Now here, the distance for traveling backwards is from here. They said at t is equal to 40, the particle starts to travel back to O, coming to rest at this. So this one here, from here to t, that is traveling backwards, okay? So here I'm going to have the distance traveled backwards is the area of this triangle. So I have a half times, the base here is going to be t minus 40, then times its height. This one here is this one we have gotten the minus 10, but you don't put minus here because we are taking this one as a length, and length cannot be what? A negative. Okay, now what do we get here? This is 10, then times 25, that will be 250. And then this is 400 divided by 2, you will get 200. Then here, this will be a 5. So we have 5t, then minus 5 times the 40, we shall get 200. So meaning our t will be equal to, this one will give us 450. Then we add the 200. Then from there we divide by 5. So is this one 650? Then divide by 5. Okay, 5 goes into 65 13 times, and then I will also put that 0. So t is 130. And then part B, find the acceleration of the particle from t is equal to 50 to t is equal to t. So from here to here. Okay, now acceleration, remember, is equal to v minus u over t. Okay, now the final velocity is going to be 0 because this particle is coming to rest, and you can see here v will be 0. So we shall have 0 minus, now the initial velocity here, it is coming from the negative 10. Okay, so I'll put that negative 10 there, and then we divide by the time taken is 130 minus 50. Not so. The total here is 130, then subtract off the 50 here, which gives us 80. So this one will be 10 out of 80. That means that acceleration is 1 over 8, which is the same as 0.1825. So you can write it as a decimal or as a fraction. It is all up to you. So that is that. Question 4 is from connected particles. 3 blocks P, Q, and R of masses 25 kilograms, 20 kilograms, and m kilograms respectively are held in equilibrium by 3 light inextensible strings OP, OQ, and OR. The strings OP and OR both pass over small fixed smooth pulleys A and B respectively, with P and R hanging vertically below the pulleys. Then the block Q hangs vertically below the point O. The angle between OA and the vertical is 30 degrees, this one here, and the angle BOQ is alpha. Find the value of M and the value of alpha. Now these are connected particles. We need to identify the forces that are acting on these particles. Okay, then after that, the forces that are not, let's say, vertical or horizontal, we resolve them. Okay, all right, now let's look at this one here. I will say, since this one is a string, then there is going to be tension in that string. Maybe that one is going to be T1, and this one here is going to have weight. Weight acts downwards, and weight is equal to mg. So this will be 25 g. This one here will be 20 g. This one here will be mg. Are we there? Okay, since this one is the same string, okay, then even this one will have a tension. So that one is going to be T1. Okay, there will be that tension T1. And then looking at this one here connected to O, there is going to be another tension here, which can be T2. You see that? And this is another string connecting here. So that means that one can be a T3. So we have T3, and it is the same that pulls out this T3 here. Okay, and it is the same string that will actually pull down this, the same tension T3 there. You see that? Now, what we are going to do is to resolve the forces. So all of these ones are not resolved. You see that? Now, when I put a, let's say, line here, that line is going to be dotted such that it doesn't interfere with our diagram. And then we resolve. The same thing I'll do, let's say here, make it dotted, just like that. Now, I'll put this one here. I'll resolve it here. Or this one, I can even put it here, but since this one is the angle, then I'm going to take this line here. Okay. Now, relative to this angle here, this one is going to be the opposite. This is the hypotenuse. Also, opposite and hypotenuse using SOHCAHTOA, that is sine. So meaning the horizontal component here, it is going to be T sine of alpha, T3 sine of alpha. And then the vertical one here, okay, this one is going to be the hypotenuse and the adjacent, that is cosine. So we have T3 cosine of alpha. Then when I come to this one here, okay, I can resolve the forces. When we resolve the forces here, you will pardon me here. This force here is supposed to be going down. Okay, it is supposed to be going down because I'm bringing this one here. Okay, I'm putting it on this vertical, and then I'm also putting it on the horizontal, okay, which is this one. So it has to be facing where? Down. And I've already said, if you have been following me, that closing is cosine because you are putting hypotenuse onto the adjacent. You see that? So we had to put this one facing down. Then when I look at this one here, resolving it, I'll close it to this one. When I close it there, it is a cosine. So we shall have T1 cosine of 30 degrees. Okay, and then I'll open it up onto this one, so that will be a sine. So we shall have, it will be facing this way, T1 sine of 30 degrees. You see that? Is there anything left? I think those are the ones that we are having. Now, resolving the forces vertically, let's look at particle P. We can see that T1 is equal to 25G, which is actually 250. These ones are equal. Remember, the system is held in what? In equilibrium. That means there is no resultant in the verticals and also horizontal. Okay? Then when we look at R, T3 shall be equal to mg, which I can say 10m. Now, at O, at point O, let's go to point O. At point O, we are still resolving forces vertically. we can see that T1 cos 30. Okay, are you seeing it? This one here, T1 cos 30. This one looks ugly. So T1 cos of 30 degrees. Then this one is equal to the forces that are going down. There is this one here. Okay, there is this one here, and then there is also this one here. Now at O here, when you look at this Q, this tension that is here, there is even another tension that is put on this O, which is also T2. You see? So they can even cancel out. The same here, I can put that T3. Okay? You can pull this one back as it takes this one here. Okay? That's why I have here, and then I also have here. The same tension that is opposing here is the same that is taking this one here. Okay? So, now when we come back here, T2 actually here, I didn't write for Q. When you look at Q, this T2 shall be equal to the 20G, which is 200. Okay, this one is equal to that. Now, meaning the total forces, okay, that the net force that is actually acting at O, already this T2 cancels out with this one. Okay, that means we have this one going up, it is only one, and the ones that are going down, we shall have T3 cosine of alpha, and then the 20G. Okay, so we shall have T1 cosine of alpha, which is equal to T3 cosine of alpha, then plus 20G. You see that? All right. Then what else? So we can simplify this one. T1 is 250. Then cosine of 30, which is root 3 over 2. Then is equal to T3. T3 is here, 10m. So 10m, then cosine of alpha, then plus the 200. Okay? So can't we now get the cosine of alpha from here? 250 divided by 2, that is 100 and... Is that 125? Root of 3? Yes. That is 125 root of 3. Then minus the 200. Then we shall divide by 10m. That will be our cosine of theta. So I can keep it. Then we shall also look at resolving forces horizontally at O. Okay, so at O, we can see this one going this way, and then this one here. I think those are the only ones that we have. So T1 sine of 30, T1 sine 30 degrees is equal to T3 sine of alpha. So meaning sine of alpha can be equal to T1 is 250. Then sine of alpha is a half. Then out of T3, which is 10m. So meaning we can have 125 out of 10m. So that is going to be our sine of alpha. So I have the cosine of alpha and then the sine of alpha. That means I can solve these two simultaneously to get alpha. So this is equation 1. This is equation 2. So dividing equation 2 by 1, by equation 1, then we shall get sine of alpha over the cosine of alpha. Then this one will be equal to 125 out of 10m, then divide by 125 root of 3 minus 200 out of 10m. So when I multiply by the reciprocal of this one, 10m will disappear, and sine over cosine is tan. So that means we shall have 125 out of 125 root of 3, then minus 200. So meaning alpha is going to be equal to the arctan of 125, then out of 125 root of 3 minus the 200. So our answer here is going to be arctan of 125 out of 125 root of 3, then minus 200. And then this one will give us 82.5. 82.5 degrees. That is 1 decimal place. Then to find m, I'll say maybe using the second equation, I will say m shall be equal to 125, then out of 10 sine of alpha, which we have gotten. So putting this one in the calculator, then m is going to be equal to, I'll leave that answer there, and then I'll say 125, then divide by, this is 10, then sine of alpha, which is this arctan here, okay? And then I'll just come here and then put the word, close the bracket, close these brackets here, just like that, and the answer becomes 12.6 kilograms. This one is to 3 significant figures. So this has been it for this first part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next videos.